Okay, so in this lesson, we're going to look at rational functions. In particular, though, we're going to look at determining the domain of rational functions and also the relationship between the restrictions and the vertical asymptotes. Now, I'm going to talk more about what I mean by that as we go through the lessons. But let's kind of review the idea of rational functions. We did spend a brief amount of time on determining the domain of rational functions in a previous lesson. So part of this will be review and part of it will not. But let's remind ourselves about the definition of a rational function. So remember, a rational function is a function that is a ratio of two polynomials. So a rational function is the ratio of two polynomials. It has to form some function name, f of x, g of x, h of x, whatever the name may be. But notice that you'll have a polynomial divided by a polynomial. Now remember, when dealing with a rational function, the denominator can never be zero. So keep that in mind as we discuss the idea of domain and vertical asymptotes. All right, so here's some examples of rational functions. And so you may recall this from a previous worksheet that you did when you found the domain of rational functions. So here's an example. Notice that we have this particular rational function, f of x equals 3 divided by x. We have a monomial divided by a monomial. So remember, a polynomial can be a monomial. In g of x, we have x plus 2 divided by x squared minus 5x plus 4. So we have a binomial divided by a trinomial. And over here, we have x to the 6th plus 5x to the 4th minus 3x. Let me just go ahead and put, let's say, plus 6 divided by 3x minus 2. So a polynomial doesn't necessarily have to be a monomial, a binomial, or a trinomial. It could be any polynomial. So any amount of monomials added or subtracted from each other. So notice that the numerator and the denominator is a polynomial. And again, as we just mentioned, the polynomial may be a monomial, a binomial, a trinomial, or just any other polynomial. Okay, now just a reminder. So notice the difference between remember what a polynomial looks like and what a polynomial does not look like. So these are examples of rational functions. A polynomial divided by a polynomial. This is not a rational function, so this is not. Even though the numerator is a polynomial, the denominator is not. Same thing here. The numerator is a polynomial. It has one term, a monomial, but the denominator is not. So remember, a polynomial, in particular, if you look at all these polynomials in the numerator and the denominator, except for the constant, the exponent of all of the variables is a whole number. All right, so the exponent is a whole number. It's either 0, 1, 2, 3, and so on. So here's 2, here's 1. This exponent is 6, this exponent is 4, this exponent is 1. The constant has degree 0. This exponent is 1. There you have your constant. So that will be degree 0. So notice, though, that this is a square root. All right, so if I rewrite this, remember the square root of x minus 4, I can write as x to the 1/2 minus 4, okay? So from a previous course in terms of rational exponents. So notice that 1/2 is not a whole number. So that's why this is not a polynomial. And the reason this is not a rational function is because this is not a polynomial. All right? Same thing here. This is not a polynomial. The exponent is not a whole number right here. All right, that's 2/3. 2/3 is not a whole number. All right, so just keep that in mind when you talk about rational functions, what it needs to look like. All right, so let's look at this. So this part here that we're looking at, so you had a worksheet on finding the domain of rational functions. And so remember, when you found the domain of rational function, you just really looked at the denominator. You found out, well, what makes the denominator 0? Okay? And so let's kind of review this. So So you're only interested in what makes the denominator 0. It doesn't matter if what the numerator is. The numerator can be 0. It's just that the denominator cannot be 0. So all you did, if you recall, when finding the domain of this particular rational function, f of x equals x plus 5 divided by x minus 2, you set the denominator equals 0, and you solve for x. So you solve this linear equation, you got x to be 2. So that's your restriction. So what we found is that the restriction is that x cannot equal 2. Because if x is 2, notice what you have. If x is 2, you have 2 plus 5, which is 7. I'm going to put that here. 7 divided by 2 minus 2, which is 0, which is undefined. All right, so that rational expression is undefined when x is 2. All right, now remember, though, how to write the domain. So in the previous worksheet, you wrote the domain in interval notation. Okay, so the interval notation, here's interval notation. And remember what you did. So basically on the number line, you kind of did this on the number line. You kind of, in your mind or even on paper, you put 2 on the number line and you crossed it out because you couldn't use it. And what that then did was it divided the number line into 2 intervals. And so that will be your domain. So your domain will be any real number except 2. That's what this means. So any real number except 2. So in interval notation, you said negative infinity to 2, in parentheses, union 2 to infinity. Okay? Now, I want you to know something about set builder notation. So set builder notation. So sometimes in my math lab or on a worksheet or in a test, you may be asked to write this in set builder notation. So in other words, just write as a set instead of interval notation. So the domain in set builder notation would be, and you write as a set. So let me put this a little bit better. So you're going to use your little braces like this. So this is the notation for set. And so you're going to say the set of x's, since my variable is x here, set of x's such that, so remember this vertical line right here means such that, so the set of x's such that x does not equal 2. And that's all you do. So that's set builder notation. So your domain in set builder notation reads as this. So this is how you read this. So it's read as the set of x's, or the set of real number x, set of real number x, such that, this right here means such that, x does not equal 2. Okay? All right. So that's the domain of this. So notice that when you found the domain of the first function, the first rational function, you wrote it as either interval notation or set builder notation. So make sure you follow the directions. The directions may say write in interval notation. The direction may say write in set builder notation. It may say both. Okay, so know how to write it. All right. Now make sure, some of you, if you become too lazy, you're going to put this in parentheses, and that's not set builder. So set builder has these braces that look like this. Okay. All right, let's look at part B. So again, when finding the domain, it does not matter. It does not matter what the numerator is. So the numerator can be 0. It's just that the denominator cannot be 0. So all we do is set the denominator equal to 0, and we solve this equation. So when we set this denominator equal to 0, this was linear. Now we have this quadratic. Now this quadratic equation is easy to solve, but that's the difference of 2 squares. So I could factor. In fact, if you think about it, you can even notice that I can use the square root property just by bringing 9 to the other side and then taking the square root of both sides. And so I get x to be plus or minus 3. So I found my restriction. So my restrictions is that x cannot equal 3 and x cannot equal negative 3. All right. Now you're going to put that in the number line. So negative 3, 3. Put that in order. Cross those out. And then that's how you did this when finding the domain. So the domain as an interval. So as an interval, you said negative infinity. So before I go ahead and write it, notice that when I crossed out those 2 restrictions, it divided the number line into 3 intervals. So you can have 3 intervals here. Here, there was only one restriction. It divided the number line into two intervals. Two restriction divides into three intervals. So you go from negative infinity to negative 3. Union, those are parentheses. So negative 3 and 3 cannot be in the domain. So that's why you see parentheses. From negative 3 to 3, make sure you put them in order. That's 3. Parentheses, union, and then 3 to infinity. Okay, that's infinity right here. All right. Now in set builder notation, all you do in set builder notation is just say the set of x's such that, since my variable is x, the set of x's such that x does not equal negative 3 comma positive 3. And that's all you do. So it'll be any real number except those two. And that's what you found here. So your domain is going to be any real number except negative 3 and 3. Any real number except negative 3 and 3. Okay? All right, so that was a review of a quick review of what you did previously in a previous lesson. Okay, now let's look at this idea. Okay, so we talked about domain, we reviewed domain. Now let's talk about vertical asymptotes. There is a relationship. There is a relationship between the restrictions that you found and a vertical asymptote. All right, so let's go to the first thing, and then we're going to go over some of this. A vertical asymptote, notice the spelling, A-S-Y-M-P-T-O-T-E. A vertical asymptote is a vertical line that the graph comes close to but never touches. So the graph will never touch a vertical asymptote. Vertical asymptotes occur where there exists a restriction on the domain of a rational function. So you're looking at the restrictions. Now, you're going to see, though, that when finding the vertical asymptotes, it needs to be in simplest form. All right, so you're going to see an example of what I mean by that in a little while. Vertical asymptotes will always have an equation in the form x equal a. All right, so that kind of makes sense, because if you think about it, so let me just do this right here. So let's suppose this is the x-axis, y-axis, and let's suppose that this is the line here. Oops, I didn't do it very well, but let's say this is the line. Let's say this vertical line goes through x equal 3. So remember, when naming a vertical line, it's always named as x equal, and in this case is 3. So x equal some number. So remember, what that means is that every x coordinate on this line has the value 3. So this is 3 comma, let's say 5, 3 comma 4, 3 comma 3, and so on. 3 comma negative 2. So notice that all these x coordinates have the x value of 3. So that's why a vertical line, you don't see a y value in the naming of a vertical line. All right, so that's what this says. So whenever you are naming a vertical asymptote, you do need to say x equal. All right, so that's important. If all you do is just give me the number, you're not going to get full credit, because I am asking you to tell me what the vertical asymptote is. The vertical asymptote has to be an equation, and it's a vertical line. So you're going to say x equal. All right, now notice what all of this was saying here. So one thing it was saying, so here is a rough sketch. Now you don't know how to do this just yet, but here's a rough sketch of the graph of this rational function, 3x divided by x minus 5. So notice that, see this dotted line right here, that vertical dotted line, that's the vertical asymptote. So that's the vertical asymptote. So right here, we're going to call this the vertical asymptote. Vertical asymptote, A-S-Y-M-P-T-O-T-E. All right. Notice that this vertical asymptote occurs at x equal 5. So you see the equation of that line, x equal 5. And remember, you get that vertical asymptote from the denominator. So look at my denominator. So my denominator, x minus 5, if you think about what the restriction is, the restriction is that x cannot equal 5. All right, so that will be your vertical asymptote. So the vertical asymptote And the restrictions, for the most part, remember it's got to be in simplest form. You're going to see what I mean by that. And this is in simplest form. You cannot reduce anything. Um, so the restrictions, for the most part, will be the vertical asymptote. All right, and notice, see where it says right here, uh, the vertical asymptote is a vertical line that the graph comes close to but never touches. So notice right here, see this right here, the vertical asymptote? So as I go from left to right on this side, notice that as the graph here gets closer and closer and closer to this vertical asymptote, see how it's getting closer and closer to it without ever touching it. So when you graph these, when you do a rough graph, make sure it doesn't cross a vertical asymptote. Just get it close to it, but stop there because you don't want to make it cross. If you make it cross, you're not going to get full credit. All right, same thing on this side. So on this side, see how the graph gets closer and closer to the vertical asymptote, but it doesn't touch it or cross it, okay? So just draw it close enough to where it indicates that it's getting close to without even touching it or crossing it, all right? Now, one thing you're going to learn in another lesson is this. See this dotted line right here? So if this is vertical, then this is what? Horizontal. So that's a horizontal asymptote. So that's a horizontal asymptote. Okay? So that's what a horizontal asymptote look like. And the same thing. So notice that the graph gets closer and closer and closer to the horizontal asymptote. The graph gets closer and closer and closer to the horizontal asymptote. Now, one thing you're going to learn though, and I'm going to say it right now, it is true that the graph, for the vertical asymptote, the graph will get closer and closer to it, but never touch it. It can't touch it because that's where the function is undefined. But you see how this particular case, the graph gets closer and closer to the horizontal, it doesn't touch it? There are situations where the graph can cross a horizontal asymptote. All right, so there are some situations where the graph can cross a horizontal, but it will never cross a vertical. It may cross a horizontal, but never cross a vertical. And it's very easy to determine, well, how do I know if a graph will cross a horizontal? You'll see as we go through some examples later on. But in this lesson, all I want to do is get you to remember how to find the domain. And now you're going to learn how to determine what the vertical asymptote is. We're not going to graph. You're going to see some graphs, but the intent of this lesson is not to graph this. That's going to be in a couple more. Okay? Okay, so let's look at some examples. All right, now, the directions will say this. Okay, so directions will say for each rational function, there are two things you want to do. You're going to determine the domain in both interval notation and set builder notation. So that's going to be the easy part because you dealt with this before. And then part B, you're going to determine the vertical asymptotes, if any. So a rational function doesn't always have to have a vertical asymptote. Almost always, though, the ones that you're going to have will, but there are situations where it will not have any vertical asymptotes. All right? And then in another lesson, we're going to talk about the horizontal asymptotes. But for right now, we're looking at domain and the relationship with the vertical asymptotes. All right, so remember finding the domain has a correlation with finding the vertical asymptotes of a rational function. All right, so let's do the first example. So here's problem number 1. So let's suppose in problem number 1, our function is f of x equal 3 divided by x minus 5. So that's going to be an easy one. So in a previous lesson, when you found the domain of this, all you did was find, well, what makes this denominator 0? All right, so what are the zeros of this rational, of this polynomial that's in the denominator? So all you did was you set the denominator equal to 0 and you solve for x. All right, and so when I did that, that is the restriction. So the restriction is that x cannot equal 5. So therefore, in part A, the domain in interval notation, now remember what that means. So what we found is that my domain will be any real number except 5. So if you put 5 on the number line and then cross it out, you have 2 intervals that you're dealing with. So you're going from negative infinity to 5, parentheses, union, and then parentheses 5 to infinity. So remember, if it's not part of the domain, you got to use parentheses. And negative infinity, infinity always uses parentheses. And then in set builder notation, you're going to say this. You're going to say the set of x's such that x does not equal 5. That's set builder notation. Okay, so that means any real number except 5, because 5 makes this rational function undefined. So 3 divided by, and remember 5 minus 5 is 0, so 3 divided by 0 is undefined. Okay, now part B. You want to find the vertical asymptote. Well, the vertical asymptote, asymptote, and then there may be more than one. The vertical asymptote is a correspondence with the restriction, as long as this is in simplest form. So I'm going to ask you, is this in simplest form? Yes, there's nothing that can be reduced, right? So that's simplest form. So therefore, that one restriction, and you only saw one restriction, right? Only one restriction. That one restriction is your vertical asymptote. So you're going to say the answer. The vertical asymptote is x equal 5. So you guys say x equal. Because remember, the vertical asymptote is a vertical line. And you name a vertical line with x equal. So x equal 5 is the vertical asymptote. Now before we go on, let me just kind of show you what the graph looks like, just to give you an idea. Now again, you don't know how this graph looks, but here's the graph, a rough sketch of the graph of what we just found. So notice, you see this vertical line right here? And notice where it crosses the x-axis at 5, right? So that vertical line is the vertical asymptote. So the vertical asymptote is x equal 5. And notice that the graph, and you're going to see how to determine this later on, but notice that the graph gets closer and closer and closer to both the vertical and the horizontal. See that? On this, so you see there's only one vertical, right? So you're going to look at what's on the right, look on the left. So on the right, the graph is above the horizontal. Remember, that's the horizontal right here. See that dotted line? You don't know how to find the horizontal. Don't worry about that. But notice that the graph gets closer and closer to both the vertical and the horizontal on this side and on this side. See that? All right. All right. But in particular, I just wanted you to notice that domain. Remember, find the domain. So you go from negative infinity to 5, and then from 5 to infinity. So remember that. So it corresponds to our interval notation, right? So negative infinity. See the arrow? Negative infinity to, and then 5. Remember, you can't use 5. And then from 5 to infinity. Okay. So that was number 1. Okay, let's look at number 2. All right, number 2. Let me go ahead and use another sheet of paper. Sorry, so this is number 2. Okay, in number 2, we have g of x equals x plus 1 divided by x squared minus x minus 6. So g of x equal x plus 1 divided by x squared minus x minus 6. All right, now the domain should not be an issue because you dealt with something like this before. So you remember in before when finding the domain, so when you find the domain of a rational function, you're determining the zeros of the polynomial that's in the denominator. So you're finding out, well, what makes this denominator equal to 0? You're finding the zeros of this polynomial. So what makes that 0, you're going to set that equal to 0. And notice this is a quadratic equation. So you're going to factor. It'll be factorable. Now, if it's not factorable, you're going to have to use a quadratic formula for us. But for us, it will be factorable. So just go ahead and factor. So it'll be x minus 3, x plus 2. And then you set each of those factors equal to 0, right? And you solve for x. So x will be 3, and x will be negative 2. Okay? So my restrictions are x equal 3, x equal negative 2. All right? So when finding the domain now, so now the domain as an interval notation, the domain in interval notation, for interval notation, let's put this on the number line and put it in order, negative 2 and 3, cross those out, and notice that those two restrictions divided the number line into 3 intervals. And so in interval notation, you're going to say negative infinity to negative 2, parentheses, union, negative 2 to 3, union, and then 3 to infinity. All right, so those are my three intervals. So those three intervals correspond to those right here. In set builder notation, you're going to say the set of x's such that x does not equal negative 2 or 3. Okay, so all real numbers except negative 2 and 3. All right, now part B, so that was part A. So part A, let's put this as part A. So this is part A, the answer to part A. Part B, you want to find the vertical asymptotes. Well, remember, the vertical asymptotes of this rational function correspond to the restrictions if this is in reduced form. So it is in reduced form. Notice that when I factor, I get x plus 1 divided by x minus 3, x plus 2, right? And there's nothing to reduce. You agree? Nothing to reduce. So this is in reduced form. And so notice you have two factors here in the denominator. So you have two restrictions. Those are two distinct factors. So you have two restrictions. So your vertical asymptote, there are two of them because you have two restrictions. So you're going to say vertical asymptote will be x equal 3, comma, x equal negative 2. All right, now remember, you must say x equal. So x equal 3, x equal negative 2. If you don't say x equal, you're going to be very upset because you're not going to get your full points, even though that's what you intended. All right, let me just show you what the graph looks like, and that's it for that one. So the graph, though, let me just kind of show you. You're going to learn how to do this later on. But see the vertical asymptotes? There are two of them, right? So there's one vertical asymptote. See this vertical line? And you're going to see that when you graph when you're asked to graph the vertical asymptote, you can do a dotted line. So this is x equal negative 2 right here, and this is x equal 3. All right, so the two vertical asymptotes, and notice that the graph gets closer and closer to the vertical asymptote without crossing it. See, vertical asymptote without crossing it, vertical asymptote without crossing it, vertical asymptote without crossing it. Now, one thing you're going to learn is that, see how this, between these two vertical asymptotes, you see how there are three intervals here? 1, 2, 3. 1, 2, 3. See how negative infinity to negative 2, you have part of your graph. And then from negative 2 to 3, your domain, negative 2 to 3, you have a graph. And then from 3 to infinity, you have a graph. Okay. And each part is continuous. Now notice, I want you to notice, see how here this graph crossed the horizontal? All right. So there are times you're going to learn about this later on, where the graph may cross the horizontal asymptote, but it will never, never, never cross the vertical. The graph will never cross the vertical because that's where it is undefined. All right. The graph may cross the horizontal, but it will never cross the vertical. So let me write this down. The graph of a rational function can cross the horizontal asymptote, but never, as you see here, but never, never cross the vertical, because that's where it's undefined. All right, so it's not part of the domain. Okay? All right, so that was number 2. Okay, let's look at number 3. All right, number 3, we have this function, number 3. We have h of x is equal to x minus 2 divided by x plus 4. All right, so that's a simple one because first of all, it's in factored form already. There's nothing to reduce, and there's only one factor in the denominator. So all I got to do is find out the zeros of this polynomial that's in the denominator. So let's talk about the domain. So to find the domain, first of all, I'm going to take this polynomial, set it equal to 0, and find the zeros. And so that's easy because that's linear. So I found the restriction. So the restriction is that x can equal -4, right? So we put that on the number line, cross it out, and so notice that this restriction, there's only one, divides the number line into two intervals. So therefore the domain in interval notation is from -infinity to -4, union -4 to infinity. In said builder notation, you're going to say the set of x's such that x does not equal -4. Okay? Now, so that's part A. Part B, the vertical asymptote, and there's just one here, right? Because there's only one restriction. And so the vertical asymptote is x equals -4. So your vertical asymptote, you must say x equal. And so x equal this -4. Let me just kind of show you real quick what the graph looks like. So remember, there's only one vertical asymptote, right? So here's the graph of what we just did. So you see that vertical asymptote right here? So there's your vertical asymptote, x equal -4. All right, that's this right here. And notice the graph gets closer and closer to this vertical asymptote on this side. And on this side, the graph goes down closer and closer to the vertical asymptote. This is a horizontal. This is a horizontal asymptote. You don't know how to find that yet, but it's easy to find. And notice that on, so remember you had two intervals for the domain. So from -infinity to -4, here's part of the graph. And then from -4 to infinity, here's the other part. All right, so on this side, the graph is above the horizontal, goes towards the vertical and the horizontal like this. And on this side, the graph is below, goes towards the horizontal, towards the vertical, like that. In this case, notice the graph does not cross the horizontal. All right. It may, sometimes it does, but not in this case. So for this function, the graph does not cross the horizontal. Notice in both cases, it got closer and closer to without crossing it. It will never, 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 never cross the vertical because that's where it is undefined. All right, let's look at number 4. So number 4, we have this number 4. All right, number 4. So we have k of x equals x plus 3 divided by x squared minus x minus 12. Okay? All right, so let's first of all go ahead and factor this. So when I factor this, I'm going to get x plus 3 divided by, and then this becomes x plus 4, x minus 4, x plus 3. And those x plus 3s, they have something in common, right? So I'm going to go ahead and rewrite this over. I'm going to leave it like this for right now. I'm going to just rewrite this over. I'm rewriting it over, and then I'm going to reduce it. These reduce out, correct? Divide out. And so you get 1 divided by x minus 4. Okay, so notice that this function simplifies to this. All right, now we got to have a discussion here because this is the first time, this is the first example where you had to reduce common factors. Okay, so let's talk about the domain. The domain. So to find the domain, you take the denominator and you find the zeros of the polynomial. Okay, so go to the original. You must go to the original. Don't go here. Don't go here. When finding the domain, always go to the original function. And you set the denominator equal to 0. You're finding the zeros of this polynomial. You factor just like we did here, x minus 4, x plus 3, okay? And then you set each factor equal to 0, just like we did. And you got 2 restrictions, correct? 2 restrictions. So my restrictions is that x cannot equal 4 and x cannot equal -3. We're going to put that on the number line in order, cross those out, and notice that my domain will consist of 3 intervals. 3 intervals. So when you find the domain, you're finding the restrictions. You got to use the original rational function. And so in interval notation, you're going to say -infinity to -3, union, -3 to 4. Notice the order matters, so make sure you put it in order. Union 4 to infinity. All right. Now, in set builder notation, you're going to say the set of x's such that x does not equal -3, comma, or 4. Okay? All right, now listen carefully to the next. Vertical asymptotes. Okay, now remember there was a statement we made earlier. Just quickly find it. There was a statement we made earlier that said, real quickly, I'm sorry, let me just kind of find it. All right. All right, and so the statement said this, right here. Vertical asymptotes occur where there exists a restriction on the domain of the rational function in simplest form, okay? So here's what I mean by that, simplest form. So do you see that when I factor this, this could be reduced, and so this is in simplest form. Notice though, what was reduced? The x plus 3's, right? So this was my reduced. So see this right here, x equal -3? That's not part of this anymore. So my vertical asymptote is only going to occur here. So let me write that down. So notice that in this problem, I reduced. Okay, I reduced. So the reduced rational function, and I'm going to write it like this: k of x equal 1 divided by x minus 4. So the reduced, so this right here reduces to this. So the reduced rational function only has one vertical asymptote and not two. Only has one. Only has one vertical, I'm going to put it as VA, vertical asymptote. And so the answer is going to be x equal 4. So x equal 4 is this restriction. This restriction is the only vertical asymptote because I reduced the x plus 3's. So you're still going to use, to find the domain, you're still going to use those restrictions. Okay, so the domain is still all real numbers except -3 and 4, except you're going to have a vertical asymptote at 4. All right, so here's a vertical asymptote, but note at the other restriction, all right, listen carefully. You're going to learn about this later on, but I'm writing right now. I'm going to write this right now. But note at the other restriction, x equal -3, there is a hole in the graph. There is a hole in the graph. So rather than being a vertical asymptote here, it's going to be a hole. Okay, so listen carefully. There are two restrictions, right, in the domain? Two restrictions. All right, you found your domain very easily. But I reduced. So since I reduced, that restriction that came from that common factor is no longer a vertical asymptote, but it is instead a hole. Okay, you're going to do a little bit more of this when we start graphing these, but here's what the graph looks like. Let me just quickly show you. Okay, so remember there's only one vertical asymptote, right? Even though there are two restrictions, I reduced. So therefore, only one of those restrictions is the vertical asymptote, and the other, therefore, is the hole. And here we go. Here's the hole right here. See what the graph looks like? So when you graph this later on, you can see how to do this. Very easy. Here's the only vertical asymptote, x equal 4. So x equal 4 is the only vertical asymptote. See x equal -3 right here? There's a hole at x equal -3. you're going to find out, you will learn very easily, and it's easy to do. It's just like using a t-table. You're going to determine very easily the coordinates of this hole right there. But that's where the hole is. So notice the graph goes towards that vertical asymptote, goes towards the vertical asymptote, goes towards the horizontal, but there's a hole now. In all the previous examples, you did not see a hole, right? There was no hole, H-O-L-E. There was no hole in any of those previous examples because we could not reduce anything. Nothing was reducible. Now we have something that's reducible. This I could have reduced, and that's what you saw here. So the x plus 3's divide out. So that means this negative 3, which is a restriction, is not a vertical asymptote, but instead a hole. All right. So it's very easy to do. Very easy to do. All right, let's look at number 5. Number 5, we have this in number 5. We have, f of x is equal to x squared plus x minus 12 divided by x plus 2. All right, so let's find the domain. Oh, well, first of all, let's go ahead and factor this. See if I can reduce anything. The numerator is factorable. The numerator is x plus 4, x minus 3, and then divide by x plus 2. So nothing's reducible, right? So whatever restriction I get is going to be a vertical asymptote since I didn't reduce anything. Okay, so domain. Remember, all you did, it doesn't matter what the numerator is, you're looking at the zeros of the denominators, which is what makes this rational function undefined. So a rational function is undefined when the denominator is 0. So you're finding the domain, the zeros of the polynomial that's in the denominator. And if you solve for x, you get x to be negative 2, so there's your restriction. There's only one restriction. We also know, since nothing was reduced, that this restriction is going to be your vertical asymptote. So the restriction at x cannot equal negative 2, cannot equal negative 2. On the number line, this restriction divides the number line into two intervals. So your domain in interval notation is negative infinity to negative 2 union negative 2 to infinity. All right. And then in set builder notation, you're going to say the set of x's such that x does not equal negative 2. Okay? And then part B, your vertical asymptote. Remember, your vertical asymptote corresponds to your restriction as long as it's not reduced. So there's nothing reduced here, so this restriction is going to be your vertical asymptote. You're going to say x equal. You must name it as an equation, a vertical line. So you're going to say x equal negative 2. The graph looks like this. So you see now this time this is the graph, and you may say, well, what is this slanted dotted line right here? Well, first of all, I want you to notice the vertical asymptote. So we just found the vertical asymptote to be x equal negative 2. There it is. And notice that the graph goes towards the vertical asymptote on this side. Now, you don't know how to do this yet, but notice, you see this slant right here? This is called a slant asymptote, or oblique, O-B-L-I-Q-U-E, asymptote. Don't worry about how to find it. All I wanted you to know was that when you looked at the graph, here was the vertical asymptote right there. But that's what the graph, a rough sketch of it, looks like. So notice notice that on this side, on this side of the vertical asymptote, the graph goes towards the vertical, goes towards the oblique. Remember in the other examples, it went towards the vertical, towards the horizontal, towards the vertical, towards the horizontal. There's no horizontal here. You don't know why, but there's no horizontal. It's an oblique asymptote instead. Nose goes towards the vertical, towards the oblique, towards the oblique, towards the vertical on this side. Now, I want you to always keep in mind about the domain here. So remember, the domain goes from negative infinity to negative 2, and then from negative 2 to infinity? It kind of makes sense from the graph, right? So look, see right here, this is pulling it towards negative infinity idea. So you go from negative infinity to negative 2, and then from negative 2 to positive infinity. Okay, now finally, let's look at number 6, and then that should be enough to get you through a basic understanding of the relationship between restrictions in the domain and the vertical asymptote. All right, this is number 6. All right, so number 6, you have x squared. So let's say g of x equals x squared divided by x squared plus 4. So x squared divided by x squared plus 4. Okay, so we got to find the restrictions, right? So well, first of all, we're going to find the domain. And to find the domain, we're going to determine the zeros of the polynomial that's in the denominator. And some of you may recognize, hey, this is the sum of two squares, and the sum of two squares cannot be factored. That's true. Some of you may say, well, okay, so what if the sum of two squares can be factored? Remember, you're trying to find out what makes it 0. So think about this very easily. Is what squared, what times itself squared added to 4 is going to be 0. Some of you may say, well, what about negative 2? Well, not quite, because negative 2 times itself is a positive 4. 4 plus 4 is 8. So another way you could think about this is this. If you get x squared by itself, you get this, right? And then some of you may go even further and say, oh, I'm going to take the square root of both sides. But even before we do that, I want you to think. Remember, when you square a number, it's either positive or 0. It's never negative. So there's no real number squared that's going to be negative 4. There is no real number squared that is ever going to be negative. In particular, negative 4, that is ever going to be negative. Because when you square a number or 0, it's either 0 or positive. Some of you may go further, though, and remember this. Well, if you take the square root of both sides, you get x to be plus or minus 2i. So right away, you notice that this is not a real number. Not a real number. So therefore, there are no restrictions on the domain. So no restrictions on the domain. There are no restrictions on the domain, which means that my denominator is never 0. The denominator is never 0. So that means g of x is never undefined. If the denominator is never 0, then this function is never undefined. And so therefore, this is what it means in terms of the domain. So that means that the domain is any real number. So in interval notation, since there are no restrictions, you're going to say negative infinity to infinity. Negative infinity to infinity. Okay? So that's the answer for part A. In set builder notation, you're just going to say this. In set builder notation, you're going to say the set of x's such that x is any real number. So the set of x is such that x is an element of the reals. Remember, capital R like this means reals. All right? Now, since there's no restriction, next question is, what's a vertical asymptote? Well, since there's no restriction, there is none. So there are no vertical asymptotes. There is no vertical asymptotes since the denominator is never going to be 0 because there's no restriction. The domain is any real number. So there are no restrictions, so there's no vertical asymptote. Let me show you real quickly what the graph looks like. So remember, there's no vertical asymptote, right? So here's the graph. Do you see a vertical asymptote anywhere? Nope. All you see is a horizontal asymptote. All right, and notice that the graph goes towards the horizontal asymptote without crossing it in this case. All right, so that is the idea behind um, the relationship between a vertical asymptote and the domain. So remember the restrictions. The restrictions are going to be your vertical asymptotes unless it is reducible. And so your restrictions here, there were two of them, right? But I was able to reduce. So these two factors that reduce here, x plus 3, this right here is not going to be a vertical, it's going to be a whole instead. The other thing I want to remind you is from what we discussed is that not all rational functions will have vertical asymptotes. You saw in this case that since the denominator is never going to be 0, then that means the domain's all real numbers and there's no restrictions, so there's no vertical asymptotes. Okay, so that is our lesson on domain and vertical asymptotes.